All right, here's some bonus material from section 4.1 where we first learned about exponential functions. And this is, I guess the idea here is this is kind of a real world example, but it's not really, as you'll see. Everything I tell you is going to be true. It's just I'm describing an impossible situation. So the idea here is we're going to take a piece of paper, a standard piece of binder paper if you want. And it's really thin because it's paper. Apparently it's approximately 0.1 millimeters thick. Fine. And we're going to fold it. And by fold it, I mean fold it in half. If you fold it in half, it's now twice this thick, right? It's 0.2 millimeters thick. You fold it in half again, and now it's twice that thickness. So I guess we'd be up to 0.4 millimeters thick. And the idea is we're going to keep folding this paper in half over and over and over again. And each time we fold it in half, the thickness of this paper will be double what it was previously. And so what we can do is we can come up with a function, t for thickness, as a function of x, where x is the number of times you fold it. And what it'll be equal to is the 0.1, which is how many millimeters thick it begins, times 2, because each time we fold it, it doubles to the x power. So after I folded this thing, I don't know, t of 50 would represent the thickness of the paper after I fold it in half 50 times. But the problem with t of 50 is it's kind of unrealistic. I mean, try it. Grab a piece of paper and try folding it in half 50 times. You'll fail. You won't be able to do it because it kind of gets too thick. The paper's not wide enough that you can't keep folding it in half. You kind of friction gets in the way. Okay, fine. So let's step out of this real life situation and put ourselves into this idealized math world. Just suppose you could continue folding it in half over and over again. It's a really, 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 really big piece of paper. So the thickness is still normal, but it's really, really big. It goes as far as you want in any direction, so you can continue to fold it in half as many times as you want. You never have to worry about it, like running out of room, anything like that. And the question is, how thick would the paper be after, I don't know, 50 folds maybe? Let's figure out t of 50. So we can do this, actually, through the power of mathematics, through the power of exponential functions. And maybe I'll make a little chart here to keep track. So folds and thickness. So when we haven't folded this thing in half at all, 0 folds, it starts out as 0.1 millimeters thick. And we fold it in half one time, and now it's 0.2 millimeters thick. And then 2 times, and now it's 0.4. And let's see how many of these we can do. 3 gets to 0.8, and you're probably bored by now. But if you're sticking around, there'll be a pretty nice payoff at the end of this thing. 5, we're up to 3.2. And then 6.4 and 12.8, and let's see how many of these I can do in my head. 25.6, 51.2, 102.4. What am I up to here? That was 5, 6, 7, 8, 9. Okay, 10. That's good. Gotten 10 of them out of the way. So after 10 folds, I'm up to 102.4 millimeters. Maybe that doesn't have a whole lot of meaning to you because you're American, you're not used to dealing with meters, or just 102 millimeters is hard to fathom even if you're comfortable with the metric system. What I want you to note is this is 0.1 meters. So maybe you have a decent idea of how big a meter is, 3 feet-ish if you're American. And so this is 0.1 meters, a tenth of a meter. So to give these things some context, 0.8 millimeters is about how thick a fingernail is. So if you're trying to keep in your head how thick this stack of paper is, or this one paper folded in half this many times, after 3 folds we're up to fingernails. And your hand, I said my hand, someone's hand, width, so from like your pinky to your thumb, I guess if you want to think about it that way, is about 10 centimeters. Well, let's see, 10 centimeters, I kind of screwed with my units here, but I can fix that. That's 100 millimeters. 100 millimeters, that's what I came up with right here. This is a hand, maybe hand thickness, hand width. So okay, after 10 folds, we're up to the width of a hand. So where are we going to end up with after 50 folds? Well, it turns out that we can figure this out relatively easily. We can do kind of some shortcuts. Really, I shouldn't have said this equals 0.1 meters. I should have said this is approximately equal to. So maybe now it's a wavy equals sign, 0.1 meters. But I'm going to assume, I know 100 millimeters is 0.1 meters. I'm going to assume it's exactly 0.1 meters. And the reason I'm going to do that is because then I can copy down this chart kind of thinking about it like I'm starting over. Instead of starting with 0.1 millimeter, I'm starting with 0.1 meter. So after one more fold, I'll be 0.2 meters and so on. So I know that after 20 folds, I will be up to 102.4 meters. So instead of dealing in millimeters, I can deal in meters because this was my starting spot and I folded that in half 10 times. So 102 meters, well, let's see, let's put that into a little bit more context. Maybe I can put in some intermediate spots here. After 14 folds, let's see, 0.1 meter, folded in half, 4 more times, I'd be up to 1.6. 1.6 meters. Let's see, that's Joe. Joe is 1.6 meters tall. Two-story house is 13 meters tall. Turns out that that'll happen after 17 folds. After 17 folds, I'd be up to 12.8 meters, which is approximately a two-story house. So already this is getting kind of amazing that after only 17 folds, our paper thickness is as tall as a two-story house would be. Kind of wild. But then we continue and we get up to 20. And after 20, as we saw before, we're up to 102.4 meters. What's 102.4 meters? Well, it's a quarter of the height of the Sears Tower. The Sears Tower is 440 meters. I'm up to 102 meters. So I'm almost a quarter of the Sears Tower. Sears Tower is pretty damn tall. So that's kind of impressive. And I'm only up to 20 folds. All right, so what about more folds? Well, after 26 folds, I'd be up to 6.4 kilometers. So I can kind of switch this. I can go do my same little tricks. Instead of calling this roughly 100 meters, I could say it's roughly 0.1 kilometers. And then I can go through this analysis again, right? I'm just changing my unit every time. So if I get up to 26, I just have to look at my list 6 here and say if I folded 20 6 more times, I'd go from 0.1 kilometers up to 6.4 kilometers. 6.4 kilometers, how tall is that? Well, now we're getting close to Mount Everest. I think Mount Everest is 8 something kilometers. I don't know, close to Everest. After 26 folds, we're almost as tall as Mount Everest, the tallest mountain on Earth. Crazy. 30 folds? Well, 30 folds would be back to this number again, 102.4 kilometers. So what is 102.4 kilometers? Now we're talking about the outer reaches of our atmosphere. Which is pretty wild, and I can jump ahead. Jumping by tens is the easiest way to go. Note that each time what I'm doing is I'm moving my decimal place 3 spots to the right. All right, so instead of 0.1, I move it to the right 3 times and get up to about 100. So from 20 to 30, I move my decimal place to the right 3 times. So instead of 0.1, I'm 100 basically. And so from 30 to 40, I'd move my decimal place to the right 3 more times, and I get 102.400 kilometers. What's that? 102,000 kilometers? 102,000 kilometers sounds like a lot. I don't have anything to put it into context with. But if I move the decimal place 3 more times, I'm 102,400,000 kilometers. It turns out that that is roughly the distance to the sun, or so Wikipedia tells me. You do this 60 times. Tack on 3 more zeros, approximately. Now I'm talking about the outer reaches of our solar system. We get up to 65 times, we're up to a third of a light year. We get up to 75 and we're 377 light years. we get up to 85. And I'm not even going to bother writing the number out here. It's roughly the diameter of the galaxy. Galaxy. Crazy. You get up to 90. I'm running out of room here. At 90, we're up to 12 million light years. Which I don't really have a way to put that into context other than saying that it's ridiculously large. And you get up to 100. And by the time you get up to 100, we're up to 12 billion light years. That's hard to read. Let me try to make that a little bit neater. And now we're so big that it's hard to even fathom what that means. But if you go back up here, you'll note that the Big Bang was roughly 13 billion years ago. And light has been traveling at the speed of light for 13 billion years. Your thing of paper is now 12 billion light years tall. So roughly the radius of the universe, which is wild. So all this to say you couldn't fold a piece of paper in half 100 times, let alone 50 or even 10 times. But if you could, in this hypothetical math world, just by following this function, what you would see is that your stack of paper would get really, really, really thick. All of this to show that exponential growth occurs very quickly. Right? Something that starts out really small gets really big in a relatively short period of time. 0.1 times 2 to the 100th power is ridiculous. T of 100 is huge. Really, T of 50 is huge, but T of 100 is super huge. It is essentially the number of millimeters that the universe is wide. Yeah, crazy.